Section 8, we're going to learn how to solve a linear first-order differential equation. That's where f of t and y has this form, a function of t times y plus function of t. It has to have exactly that form, or be possible to put it in that form, or it's not linear, and if it is possible, it's linear. Notice that the y appears just multiplied by some function of t, and there's a extra term b of t there. The a and b, of course, could be constants, or they could be 0, but the y has to appear only as y. It can't be y squared or square root of y or e to the y or anything. So basically a linear problem, first order problem, is something that has this form, and if it can't be put in that form, it's not linear. And in general, this is not separable, though it could be. So we didn't learn how to solve this in section 2. So this is a first order linear differential equation, and I prefer to take this term on the other side and write this as y prime minus a of t y equals b of t. So the b of t will be by itself the non-homogeneous term b is called. And in fact, if b is 0, this is called a homogeneous linear equation. So and if b is not 0, it's a non-homogeneous problem. Okay, how do you solve such a problem? Well, we're going to show that if you have any solution to a solution to the homogeneous equation y sub h, and any particular solution of the non-homogeneous equation, the general solution of the non-homogeneous equation, in other words, the original problem, is c times the homogeneous solution plus y sub p, the particular non-homogeneous solution, where c is an arbitrary constant. Now you might say, well, if we have a particular solution, what do we need that for? Well, we need the general solution. We're generally going to have an initial condition, and you have to have the general solution before you can impose the initial condition. So we don't just want any solution. It sounds like, saying there's 2 steps, and step 2 is solve the problem. Well, not exactly. It's close, but step 2 is to find any particular solution by hook or crook any way you can, and you're not through. If you find any particular solution, you're not through. You have to find the homogeneous solution and add an arbitrary multiple of that to get your general solution. And to prove that that is the general solution, or that is a solution and it has one arbitrary constant in it, it's a first order problem, so you expect a general solution to have one arbitrary constant in it. You need one constant to be able to satisfy the one initial condition. But so if y sub h is a homogeneous solution, that means you plug it into the left-hand side here, you get 0. Y sub p is any particular solution, that means you plug it in here and you get b. Then put them together with any constant c and you'll get b, basically because plugging this into the left-hand side of that gives you 0, and plugging this gives you b, so no matter what c is, you get 0 plus b. And we just write that out here, y prime minus a of t y. Y prime is c, y h prime plus y sub p prime, and then minus a times y. Combine the 2 h's, and you get h prime minus a h prime y h prime minus a of t y h, and that gives you 0 because y sub h is solution homogeneous equation, so that 0 times c, and this gives you the b, so together they give you b. But you need this term because you need an arbitrary constant. Just having a particular solution, you're not done. You need the general solution, and for that you just add an arbitrary multiple of the homogeneous solution. So there's 2 steps to finding the general solution. The first one is to solve the homogeneous equation, that is where b is 0. And fortunately that's always possible to do because this is always separable. And in fact, in most of our problems, a will be a constant, in which case it's just y prime equals ay, which the solution of that is e to the at, or any multiple of that, but we've got the multiple there, so we'll just take y sub h to be e to the at, and then we've got c e to the at plus the particular solution. So the first step is usually the easier one because that's a separable problem even if a is not a constant. If a is a constant, you can just write down the solution automatically, e to the at. So you'll have a c e to the at plus a particular solution. Now, how do you find the particular solution? Well, that's the hard part. And if A is not constant, it's still true that the general solution is this, but it's a lot harder to find y sub p, and actually harder to find y sub h also. So most of our applications, A will be constant, B will not. So if A is constant, then the homogeneous solution is just e to the at, so c e to the at. Now the particular solution, well, it depends on what B is, and we're going to get certain rules which only work if A is constant. If A is not constant, you're on your own. You've got to find the y sub p any way you can, and you have to get lucky usually. But if A is constant, there are certain rules on how to find the particular solution depending on what B is, and here are the basic 4 rules. If B is an exponential like e to the 8t or any multiple of e to the 8t, and I'm just picking 8 at random here, I might prefer I put variables in there, e to the ct or something, but we've got enough constants floating around here, so I'm just going to take a specific example. And it's obvious if this is e to the 7t, you try alpha e to the 7t. So I don't think there's any confusion here, that the fact that I'm using a particular value for the exponent. But anyway, if the right hand side is e to the something t times anything, then you try alpha e to the that something t. If it's something times e to the 8t, you try alpha e to the 8t. And that seems like a reasonable thing to try, because y prime will just still be a multiple of e to the 8t. A is a constant, y is a multiple of e to the 8t. Put the two together, you get a multiple of e to the 8t, and hopefully you can adjust the constant alpha so that gives you the 3 there. And we'll see an example. And so if the right hand side is e to the 8t or e to the 10t or e to the minus 5t, then you try alpha times e to the whatever I said t. Now if the right hand side is cosine of 3t or whatever, that obviously could be anything you want to choose there, or sine of 3t, I'm just using that as an example, and any multiple out front, it doesn't matter. If you have a sine or a cosine or both, if this is 5 cosine of 3t plus 4 sine of 3t, or just the sine or just the cosine, any of those cases, what you do is you try a sine and a cosine, of course the same frequency. If this is a 3, then you put the 3 there. And so you try alpha times sine of 3t plus beta cosine of 3t. And if the right hand side is cosine of 3t or sine of 3t or any linear combination of cosine of 3t and sine of 3t, you have to try alpha e to the 3t plus beta cosine of 3t. So we can handle it if the right hand side is an exponential or a sine or cosine. If it's a polynomial, again I'm being specific about the polynomial, but I think you can figure out the general idea here. If you have a cubic polynomial, whether it's just t cubed or t cubed plus 3t squared plus 2t plus 8, or your t squared is missing, whatever, it's t cubed plus anything lower, you try a general polynomial of degree 3. Cubic polynomial. So obviously if that's t to the 5th plus 8, you try alpha t to the 5th plus beta t to the 4th, etc. You've got to do a full polynomial, all the coefficients. If this has a t cubed in it, you've got to try full polynomial degree 3. So those are the 3 basic rules. So if the right hand side is a polynomial, sine or cosine or exponential, and A is constant, then you know what to try now. And if it's something else like tangent of t, you're just out of luck. So we'll only be able to solve some specific problems, but these are some interesting ones. And then D basically says if A, B, and C don't work, multiply by t. If at first you don't succeed, multiply by t, I always say. Why? Well, why any of these rules? It's basically, it makes sense after you've tried it a while, but it's not obvious right now. So let's look at some examples. So review again the 2 steps. Find the homogeneous solution, which is easy, especially if A is constant. It's separable, and really easy if A is constant. And then the non-homogeneous equation solution, you have to either get lucky or try the right thing. And if the right thing is e to the 6t, you try alpha e to the 6t. If b of t is cosine of minus 2t and or sine of minus 2t, you try alpha sine of minus 2t plus beta cosine of minus 2t. If the right hand side is polynomial degree 2, t squared plus 2t plus 1, you try alpha t squared plus beta t plus gamma. Try a full polynomial. You have to include all the terms, even if it's just a t cubed here. And if at first you don't succeed, multiply by t and try again. Okay, let's look at some examples in the book now. Well, this is the linearity principle that I already talked about. Basically says for this linear differential equation, notice that y just appears as y. Of course, that could be 0. Then the general solution is arbitrary constant times the homogeneous solution plus any particular solution. And if you find a particular solution, you're not through, because you have to add this term to get the general solution, and you need the general solution in order to satisfy the initial conditions which normally come with it. Okay, now let's look at, the next section, by the way, we're skipping 1.9. It has a more systematic way of solving these linear problems. I'm skipping it because that only works for first order problems, and later on in chapter 3 we're going to deal with, in chapter 4 rather, we're going to deal with second order linear problems where you have second derivatives here, and then the stuff we're doing now will still work with obvious changes, whereas the section 1.9 stuff won't work anymore, so that's why we're skipping 1.9. It's not general enough. Okay, here's a first example in the book. Basically, a is minus 2 and b is e to the t, so a is constant. So the homogeneous equation is y prime equals minus 2y, so the general solution is arbitrary constant. I called it c, they call it k, times e to the minus 2t. That was easy. Now you need a particular solution of that, and our rules say, well, if the right hand side is e to the t, what do we try? We try alpha e to the t. So they tried some other things here to show they don't work, but our rules tell us, well, try alpha e to the t, because the right hand side is e to the t. If it were 4 e to the t, we still try alpha e to the t. Plug that in, and well, y prime is alpha e to the t plus 2 times y is alpha e to the t, and we get 3 alpha e to the t. And remember, we want that to come out to be e to the t, so 3 alpha has to be 1, therefore alpha is 1/3. Therefore our particular solution, alpha is 1/3, is 1/3 e to the t. That's our y sub p, and that's our general solution of the homogeneous equation. So there's the complete solution, and now we're ready to plug in the initial condition, if there is one, to find k. Notice the little difference. It looks like this alpha is an arbitrary constant here and the k is an arbitrary constant, but really alpha is not arbitrary. It's just unknown until we plug it in. Then we find alpha has to be 1/3. That's the only value of alpha that will work, whereas any value of k will work until you apply the initial condition, and then only one value of k will work. Okay, on the next page they have another problem where now the right hand side is cosine of 3t, the b term is, and well, the homogeneous equation is still y prime equals minus 2y, so the general solution of the homogeneous is k e to the minus 2t, so that hasn't changed. But now the right hand side is cosine of 3t, so our rules say try alpha cosine of 3t plus beta sine of 3t. You might say, why not just try cosine, because when you plug that in you're going to get a sine here, and you can't adjust the sine to give you a cosine. So you try a cosine and a sine, whether this is a cosine or a sine or both. You have to try alpha cosine 3t plus beta sine of 3t. Plug that in, and now this gets more complicated. This is harder than the previous one, but it's straightforward. You just plug that into the equation, take its derivative plus 2 times the function, combine the sine terms and the cosines together, and you say, well, we want this to come out to be cosine of 3t, which means the coefficient of cosine of 3t needs to be 1, and the coefficient of sine 3t needs to be 0, so that has to be 0 and that has to be 1. So we set the coefficient of sine of 3t equals 0 and the coefficient of cosine of 3t equals 1, because that's what the right-hand side is. If we had a 4 cosine of 3t plus 5 sine of 3t, then this would have to be 5 and that would have to be 4, but it doesn't matter. You're going to have to solve a system of two equations, and that's why it's messier, but you know how to solve two equations. There's the solution. So we know what alpha is and beta is, so those are the only alpha and beta that work. That's the particular solution. And you're not through, because you have to add the general solution of the homogeneous equation to get the general solution of the whole shebang. So there we are. Now we're ready to plug in the initial condition if there is one. Otherwise, that's the general solution. So that illustrates my rules 1 and 2. They don't have an example in the book illustrating the case where the right-hand side is polynomial. However, I did give you a couple of homework problems where the right-hand side is polynomial. But here, this illustrates rule D, which says if at first you don't succeed, multiply by t. So let's look at this now. The same left-hand side, so the solution of the homogeneous equation is still e to the minus 2t. But now the right-hand side, well, our rule number 1 says if the right-hand side is e to the minus 2t, we try alpha e to the minus 2t. And we plug that in, and there's a derivative plus 2 times y. It gives you 0, 0 alpha, and so 0 alpha has to be 3, which means there is no alpha that makes that 0 times alpha equal to 3. And then if you think about it, well, you could have avoided this because you know the trying alpha e to the minus 2t couldn't possibly work, because that's a solution of the homogeneous equation. So we got unlucky here that the solution of the homogeneous equation and the thing we try for the right-hand side particular solution happen to be the same. They're both e to the minus 2t. If that had been anything other than minus 2, we wouldn't have this problem. So this couldn't possibly have worked. We could have saved the trouble of even trying it, because that's a solution of the homogeneous equation. It's bound to give 0. It can't give 3e to the minus 2t. So what do? Well, you'd never figure this out, but somebody a long time ago figured it out and told their kids, and their kids told their kids, and their kids told their kids, and down to the present day, and we know from our ancestors that you multiply by t. Well, you can be a little more scientific than that, but basically just take that as a rule. In other words, if alpha e to the minus 2t doesn't work, try alpha t e to the minus 2t. Well, why in the world would you try that? Well, just because it works. And it only works when you need it to work. In other words, if alpha e to the minus 2t did work, then you not only don't need to try alpha t e to the minus 2t, but it won't work. But so we multiply by t and try, instead of alpha e to the minus 2t, which is the solution of the homogeneous equation by bad luck, we try alpha t e to the minus 2t and plug that in, and you're going to have to use a product rule now, because two functions of t is a little more work. But you end up with alpha e to the minus 2t, which is good because, remember, we want this to come out to be 3e to the minus 2t. So we just take alpha equal to 3, and there's our solution, our particular solution, 3t e to the minus 2t. And that particular solution, we have to add the general solution of the homogeneous equation to get the general solution. So your homework problems are all solving linear first-order differential equations. Some you'll have to multiply by t, like the last example. Some you won't. And these you get the general solution, so you'll have an arbitrary constant in it. These, they give you initial conditions, so once you find the general solution, you have to plug in t equals 0, y equals 1, and see what that constant has to be. The arbitrary constant has to be to make that work. And then I gave you a couple of problems where there is a polynomial on the right-hand side. In fact, this one has a polynomial and a sine of 3t. So now what do? Well, if there were just a t cubed, what would you try? I mean, the general solution of the homogeneous equation is still easy. It's just c e to the minus t, because a is minus 1. But the particular solution, there's really two parts here. if the right-hand side were just t cubed, you'd try alpha t cubed plus beta t squared plus gamma t plus delta, and plug that in and grind it out and see what alpha, beta, delta, and gamma have to be. By the way, you'll end up with 4 equations and 4 unknowns, which sounds difficult, but it actually is easy to solve because one of the equations involves only one unknown and so forth, so that'd actually be easy to solve. Now, if the right-hand side were sine of 3t only, you would try alpha sine of 3t plus beta cosine of 3t. So basically just 2 separate problems. Find the particular solution that gives you t cubed, find the one that gives you sine of 3t, and put the two together. And similarly here, that's a polynomial of degree 1, so you try alpha t plus beta. That's e to the 4t, so you try alpha e to the 4t. Find the particular solution that makes the left-hand side come out to be 2t. Find the one that makes the left-hand side come out to be minus e to the 4t. Put them together, and there's your general solution.